Cool. Okay. Well, thank you very much, guys. So my name is Michael. I'm a software engineer at Databricks, and I'm here to talk about Databricks Delta and how it can bring reliability to your data lakes. But I want to start at the beginning. Who here is familiar with the concept of a data lake? Okay, so most people. To me, what a data lake is about is it's basically this promise. So first of all, collect everything. So your organizations have tons of data in a wide variety of different formats. It could be just kind of raw telemetry from your customers. It could be voice and speech. It could be click streams. And the idea of a data lake is it should be really easy to store all of it in the data lake. It's not your traditional RDBMS. You don't have to set up a schema ahead of time. It's kind of schema on read. So you can actually collect everything in the data lake automatically. Some other really important characteristics of the data lake are it's scalable. So you can kind of dump infinite amounts of data. If you're in the cloud, it's elastic, so it's pay as you go. You can just kind of add data and only pay for what you're storing. You don't have to set up infrastructure. If you want to bring up extra clusters to read from it, it parallelizes automatically. It's a pretty compelling vision. And then the idea is, once you've got all of your data stored in the data lake, you can do data science and machine learning. And you can use that to bring value to your business. So you can build recommendation engines, you can do fraud detection, you can even do things like cure cancer with genomics. However, there's the problem here. The problem is that, in general, your data is garbage. And as a result, you're storing garbage. And as a result, you get garbage out. All of your recommendation engines are producing nonsense. And this is a pattern that I've seen play out kind of over and over again in the data lake space. A lot of people spent millions of dollars on Hadoop clusters, and those projects failed because they couldn't figure out how to get quality out of this data that they've collected. To make this a little more concrete, I actually want to walk through the steps that I've seen many organizations go through as they tried to build out a kind of a reliable, successful data lake with quality. So, this should look like a pretty standard template. Your boss comes to you, he says, there's a whole bunch of data stored in Kafka, and you need to process that, and I need two things. I need streaming analytics, so I can know what's going on in real time, and I also want to do kind of more advanced AI and reporting. So how do you build this thing? Well, I might be a little biased here, but my first instinct would be to use Spark. It's got APIs that can read from Kafka. You can use data frames, data sets in SQL to parse it and do analytics and do time windowed aggregation, and I can set up all of my streaming aggregations. So pretty cool. But that brings us to challenge number one. This kind of streaming analytics are really good at telling you what's going on in your business at this moment, but it's not very good at looking back in time and doing longitudinal analyses, actually looking back at the last 2 years, trying to train a model on that, or try to see how trends have changed over time. So what I see a lot of people do, and I've read a lot of blog posts and things, I've heard about this thing called the Lambda architecture. I guess the idea about the Lambda architecture is I'm just going to do everything twice. I'm going to have a streaming version that is really fast, but maybe wrong. And I'm going to have a batch version that captures everything, but it's slow. It's like days old. But this can work. So I see people set up this kind of Lambda architecture. Now we've solved historical queries. And so, okay, now I can query that data lake. So pretty good. But that actually brings us to the next problem, this messy data that I was talking about. So someone upstream from you decided to change the meaning of this column, and they didn't tell you about it. And now your analysis is wrong, and now there's bad data in your data lake. You're parsing it incorrect, you've got nulls in that field or whatever. And so then you kind of have to go back and you have to build validations on top of it. So you write extra Spark jobs that check the quality of the data and fire alerts if something's wrong, so you can go in and fix it. Now, we're in this Lambda architecture world, so I actually have to do it twice. I got to do validations in streaming, and I got to do validations in batch. But it's not too hard. Spark has unified APIs, so it's pretty easy. So okay, we've added validations in, pretty good. However, that brings us to the next problem, mistakes and failures. Yes, our validations are great, but sometimes they miss something. And once that data is in your data lake, how do you fix it? Once there's bad data that's been captured, it's just a whole bunch of files stored in a hard drive. Like how do you actually go in and adjust the quality? So I've seen this pattern over and over again. Basically, what you do is you break your data lake up into partitions. So you create a bunch of folders. You have directories by date or by hour or by region, something that makes sense for you. And you build an engine to do reprocessing. So if anything ever goes wrong, it's fine. I just delete that whole directory and reprocess that whole day of data. And now I have an engine to kind of deal with these mistakes. So I built a reprocessing framework. It was a bunch of work. I had to kind of build all this stuff on top of Spark, but it works out. And that leads us to challenge number 4, updates. So GDPR happens or CSSPA happens. And now you need to go back through all of your data lake all over time and update it to remove somebody who's asked to be forgotten. Or you have merge queries. You've got kind of a set of transaction data, and you want to merge those updates into your data lake. How do you do those things? Well, it turns out you have to build a lot of very complicated Spark queries to do them manually. Everyone has to build their own. And you got to be really careful about this, because if you run them at the same time as somebody querying the data lake, they're just going to see garbage. They're going to see this intermediate result. They're going to get the wrong answer. There's no isolation. But I can do it. I can build that. I can schedule it. I can make it happen. And so now I've kind of got all this stuff, but now I've built a pretty complicated architecture. And kind of the theme here is you're wasting time and money solving systems problems when what you should be doing is extracting value from your data. And just to kind of touch on this a little bit more, to kind of summarize, I think these distractions that people get caught in with the data lake are pretty common. There's no atomicity, which means that if your job fails in the middle, it's your responsibility to fix that failure. It's already written out partial results, and you have to kind of reason about that in every step of the way. You have to think about these failures and how to clean them up. There's no quality enforcement, so there's nothing preventing anybody in your organization from just dumping garbage into that table and corrupting all of your results. And then finally, there's no consistency or isolation. So if you want to do streaming and batch at the same time, if you want to mix multiple jobs reading the same table, it's very likely you're going to get the wrong answer. And so the idea of Delta Lake is we want to make it simpler for you to do these things, kind of by building a holistic system that thinks about this from the beginning. So we want to take something like this, and we want to change it to this. So now you're only thinking about data flow. You're starting with your raw data, you're incrementally cleaning it, and then you're doing your actual analyses. And Delta Lake brings a couple of key features here. The first is full ACID transactions. So I don't know if everyone's familiar with ACID, but it's atomic, consistent, isolated, and durable. It's what standard relational databases do. And the idea here is it ensures that your Spark programs will execute correctly, even in the case of failures. If something goes wrong, that transaction will either happen completely or not at all. If two people are reading the table at the same time, they will each see consistent snapshots of the table. Once something is committed, it's definitely committed. This means you're no longer thinking about those systems problems when you're writing your code. Another really important part about Delta Lake is it's based on open standards and open source. I'm going to talk about this at the end, but all the data is stored in Parquet. The format is open source. The engine for reading it is open source. And I know personally, I would be very hesitant to store petabytes of data in some black box where I could be locked in. It's very important that you can move from engine to engine, that you own your data if you're going to collect such a valuable asset. And then finally, it's powered by Apache Spark. So this means that whether you're doing streaming or batch, if you've got data frame code, data set code in Python, Java, Scala, or SQL, you can easily convert to Delta. And I'm going to talk about that later in the talk, how easy it is to convert your existing code to use Delta. But now I want to take this picture and I want to simplify it. And I want to talk about some of the kind of high-level themes that I see people kind of fall into as soon as they stop thinking about systems problems and they start thinking about these data problems instead. So a pretty common pattern is people start thinking about data quality levels. So this bronze, silver, gold, these are not specific features of Delta. These are just categories that I see people starting to classify their data in as they kind of go through this journey. And the idea is Delta gives you the tools to incrementally improve the quality of your data until it's ready for consumption. Because data is always going to be messy. There's always going to be mistakes. There's always going to be missing values. But using Delta, you can actually clean it up and get it ready so that you can actually derive value from it. So let me walk through each of these and kind of talk about the hallmarks of each class. So starting with bronze, this is kind of our tire fire that we started off with. It's a bunch of garbage. It's a dumping ground for raw data. But you can store years of it, and you can store everything. And there's actually value to storing that raw data, because there are no bugs in a parser that you don't write. So if you don't do any transformations on it, you cannot corrupt the data. So it's actually valuable to capture the raw information from the beginning and keep it all for as long as you're allowed to keep it. The next step is silver, where you've started to clean it up. You've maybe filtered it out. You've parsed the JSON. You've added some schema to it. You've maybe joined with some other information to augment it with useful details. And you materialize this. Now you might say, why am I materializing these intermediate results if they're not my end answer? And there's actually a couple of reasons for this. One is this silver data is often valuable to multiple people in the organization. And by creating this table, you can create these kind of data reservoirs where many people can go and get value from the cleaning that you did. But another reason is just debugging. When I get to the end and my report is wrong, it's super useful to be able to query these intermediate steps, and Delta makes that really easy. And then finally, we get to gold data. Gold data is cleaned up. It's high-level business aggregates. It's ready for consumption. It's metrics that matter to your business, and they can be consumed directly by Spark or Presto. You make reports in Tableau. You do machine learning on it. This is the data that is now ready for consumption. So how do you use Delta to actually construct this and move data through these different classes? So one pattern that I see over and over again is streams. Use streaming to incrementally move data through these different levels. And a lot of people are going to say, wait a second, stop right there. I don't need real-time data. I only need my reports run once a day or once an hour. And this is where I have to tell you something about streaming. Streaming is not always about low latency. Streaming is about continuous incremental processing of data. And the magic part of streaming is when you use streaming, you're no longer thinking about what data is new, what data is old, what have I already processed, how do I checkpoint my intermediate results, how do I recover from failures, how do I make sure that processing happens end-to-end with exactly one semantics. The streaming engine is thinking about that for you. You just write SQL code or data frame code, and it makes sure that data automatically moves through these different quality levels, as it arrives. And the really cool thing about structured streaming in Spark is it actually has this nice cost latency slider. So you can run your thing in continuous mode, where it's continually using a core, constantly polling for new data, and get millisecond latency. But sometimes you don't need that. And so we also have this micro batch mode, where you can kind of incrementally run tiny tasks, and now you can get minute latencies. And then some people say, no, data only arrives once a day. I want to shut the cluster down in between. And we have this really cool feature called trigger once, where you run a streaming job, it starts up, it processes everything that's there, and then it shuts down. So you can use a streaming job that only run once a day, once a week, once a month, whenever you want, and still get all of those benefits of thinking about data flow rather than schedules and jobs and failures and checkpointing, those systems problems that are distracting you from the problem you're actually trying to solve. Now, of course, streaming is not everything. Delta has full support for batch. So whether you need to, once a year, delete all of the data that is past some retention window, or once a month you get DSRs for GDPR and you need to clean them up, or if you just get batches of data that you need to insert in or merge into the table, Delta also fully supports all of the batch APIs, including standard DML like update, delete, and merge. These are all features that we're planning to open source this month in the next release. And then finally, I want to talk about one kind of other really cool pattern that Delta enables, and this is recomputation. So because we kept all of the raw data in that kind of initial bronze table, and because we're using streaming to process all this data, if I ever find a bug in my code, or if there's some new analysis that I never even thought of that I want to add to my system, all I need to do is restart the stream. Because the way a streaming query against a Delta table works is when you first start the stream, it starts by taking a snapshot of that table at the moment that the query started. It processes through that backfill of all of the data that was there when the stream starts. And once it gets to the end of that snapshot, it kind of switches modes and it starts incrementally processing new data that arrives. And the end result is you get the same result with a streaming query that you would have gotten with a batch query. It's just broken up into nice incremental checkpointed pieces, and it continually gives you the same the new answer as new data arrives. So it's really easy to do this when you want to do it. All you do is clear the data out of the table, delete the checkpoint, restart the stream, and you've recomputed everything. If you're in the cloud, you can take advantage of elasticity, and you can start up a giant cluster with 1,000 machines while you're doing the backfill and then bring it down. So for $100 or $1,000, you can recompute all of time with your data, which is pretty powerful. So who's using Delta Lake? Why is this interesting? So I want to give you a little history about the project. Delta Lake is a fairly old project now. It's been inside of Databricks for the last 2 years, and we recently open sourced it. But what that means is Delta Lake is already used by thousands of organizations around the world. Last month, we processed over an exabyte of data. And I want to talk about one particular use case that I actually think is really cool. This is COMCAST use case, because it follows exactly that bronze, silver, gold pattern that we were talking about. They collect all of the raw data from every set-top remote control, and they clean it up, they filter it, they augment it, and the end goal is to build machine learning that helps improve their kind of speech-to-text recognition. They had this running in Spark, before they moved to Delta. But what they had to do was they actually had to split it into, I guess, 10 different Spark jobs. So they had, because Spark just could not handle the scale of the metadata they were processing, they took this one query, they kind of manually partitioned it across 10 different clusters. And then when they were able to switch to Delta, because of the efficiencies in our metadata management, which I'll talk about in a little bit, they were actually able to take it from 640 instances down to 64. They run one Spark job instead of 10. That's actually really powerful, because all that time that they're spending not managing these 10 extra Spark jobs is now time they can spend building new analyses that they wouldn't have been able to do otherwise. So how do you use this thing? It turns out it's actually pretty simple. If you're already using Spark, all you need to do is add a Spark package. So there's an artifact up on Spark packages already, io.delta. All you need to do is add this argument -- packages to your Spark shell, and you've installed Delta into your Spark cluster. If you're building a Spark application, you can do it just by adding a dependency to Maven or SPT or whatever tool you're using to build. And then in your code, the transition is really easy, because Delta ties deeply into the existing data frame reader and writer APIs in Spark. So all you need to do is change Parquet or JSON or CSV or ORC to Delta, and your code will work the same, except now it's fully transactional and scalable. I want to talk a little bit more now about data quality, because I think transactions get you a lot of the way there. Transactions make sure that your code that you wrote actually runs correctly, but unfortunately, none of us is perfect. There's always bugs in our code, and you need a tool to handle that. And so another cool thing that we're actually working on this quarter is the ability to improve both the discoverability and the quality of your data. So we're creating this language where you can declaratively specify the structure of your data lake, and then we'll enforce that structure at runtime. So in this case, I'm creating this table called warehouse, and I'm defining a bunch of the basic things. I want this table stored in this bucket. I want to mandate the schema of this table. Delta has two different modes for schema. You can either do kind of automatic schema migration, where we will just automatically accept any data you throw at us. We'll make sure you don't have columns of conflicting columns arrive. Or you can run in strict schema mode, which is just like a traditional database. You write create table. We do not allow you to insert any data that does not match that schema. And if you want to change it, you have to run alter table. So you can kind of choose which end of the quality spectrum you want to be on. We're working on allowing you to register your Delta tables in the Hive metastore so that they're easily discoverable by other people in your organization. And we'll even allow you to put human readable descriptions about that table alongside it. So it can be something like, this comes from this data source. It is processed by this group. These transformations have been done to it. But the feature I'm most excited about is this concept called expectations. Expectations allow you to take knowledge that you have about your domain and apply it to your specific data science tasks. So what that means is, if you're familiar with the traditional database concept of invariance, this is invariance, but for big data. I can say something like, I expect my data to have a valid timestamp. And I can say what that means. For example, my organization may have started in 2012. So if data comes from before that, that's invalid to me. And I can express that as a predicate. And that's where invariance would stop. Basically, anything that didn't match that expectation would fail and your transaction would end. Unfortunately, in the big data space, if you fail every time you see something unexpected, in many cases, you won't get anything done. And so the cool thing about expectations is we allow you to tune that quality slider again. Kind of the severity of the expectations can be changed. So I can choose, when I get to my gold level, something that accounting is doing reporting on, do not let bad data go into that. Fail any transaction that doesn't meet my expectations. But earlier on, I can say, you know what? I just want to get an alert when more than 10% of the records don't parse. Or even more powerful, we're working on this feature called data quarantining, where what we will do is, rather than fail the transaction, any records that don't meet expectations will just be funneled off to a side table where you can come and look at them later and deal with it. So this is a really cool feature that we're basically, this is one of the key focuses for my team this quarter. We'll be releasing this API. I'll talk about this more at the end, but I would love to hear feedback on this on GitHub. So that's kind of the high level overview. That's why you should care about Delta, how you use it, who's using it for what kinds of things. But now I want to talk about some of the nitty gritty details of how Delta actually works under the covers, because some people say it sounds like too good to be true. So let's talk about what Delta actually looks like under the covers. So Delta on disk is actually pretty simple. So you've got your file system. It could be HDFS, it could be S3, it could be Azure Blob Store, something like that. And Delta is going to look very similar to your data lake today. It's a directory with a bunch of Parquet files. But in addition to the Parquet files, we have a transaction log. So there's this hidden directory called Delta log. And inside of it, there are a bunch of JSON files that match each version of your table through time. And then we, of course, have kind of the standard partition directories. I say that they're optional because we've actually also got some cool tricks where when you're running on S3, it turns out partition directories by date is an anti-pattern. It causes hotspots when you insert new data. So because Delta is managing the metadata itself, we also support randomizing prefixes so that S3 works faster. But for debugging, you can also do it this way. And then we also have your data files, which are just normal open format Parquet files. So now what's actually going on inside of those JSON files? And to explain that, you need to kind of think about what is the state of a table and how do I change it? And the way we model this in Delta is a table is the result of a set of actions. And these actions are pretty simple. The first one is change the metadata. So do something like say, this is the schema of this table, this is the partitioning of this table. And we actually support kind of relatively simple schema evolution over time. So you can add columns. If you overwrite the data, you can completely change the schema. We basically support anything that Parquet can do, and we enforce that that is done correctly. You can, of course, add data to the table. So in this case, you just say, add this Parquet file to the table, or remove this Parquet file from the table. So the important thing to realize here is when a Spark job is running, it is writing out Parquet into your data lake, but it is not part of the table unless it's also added to the transaction log. This is how we get isolation. So if your job fails in the middle, there's a Parquet file out there, and it'll just get lazily garbage collected. But it's the addition of this add file into the transaction log that actually makes it part of the table. I'll talk about this a little bit more. But in the end, if you want to know what the current state of the table is, you just play all of the actions, and you get the current metadata, a list of files, a list of transactions, and some version. OK, so how do you take that, though, and actually get ACID, all of the properties of databases? So first one is atomicity. And the trick is we actually store these changes in atomic ordered units called commits. So each one of those JSON files is an atomic transaction. And we use atomic primitives on the file system to create that file. So if you're on S3 and you're uploading a JSON file, it is guaranteed atomic. You start the upload by saying expect these many bytes. And if you don't get that many bytes, it doesn't appear. On things like HDFS or Azure Blob Store, we use atomic rename. So we create a temporary file, and then we rename it to the final destination. And that guarantees that that file will be created atomically. And so in this example, we're starting with version 0 of the table, where we add these two files. And then version 1 can atomically remove those two files and add them. Let's say you were doing a compaction because those two files were too small, and you want to replace them with one big file. This is how you would do that in the Delta system. The next question is serializability. How do we all agree on a consistent ordering for the table? So the trick we're going to use here is called mutual exclusion. So we need the underlying file system to guarantee us this primitive. User 1 can create file 0. User 2 can create file 1. But if they both try to create file 2 at the same time, one of them must fail. So HDFS, Azure Blob Store, they all provide this primitive out of the box. You can basically say rename needs to fail if the destination exists. S3, you need a service on top, and we're working on that. Now, you might say, wait a second, but if every time there's a conflict, I just fail, that sounds like I'm wasting a lot of work. And fortunately, there's a really cool trick from databases that we can play called optimistic concurrency. So the optimistic concurrency algorithm says, go forward assuming your transaction is going to commit. And if you lose that race, check to see if it actually matters. And if not, retry. So just to walk through that, let's say we have two users, and they're both appending streaming data to a table. So we start by recording the start version, which was 0. We record what reads and writes they do. So they both check the schema of the table to make sure the data they're writing into the table is valid. And then they append some data to that table. And then they go to commit. And user 1 wins, and user 2 fails. So what user 2 does is user 2 looks at user 1's transaction and says, did anything change that I care about? And the answer is no. The schema of the table stayed the same. So user 2 can just try again. So Delta kind of does this automatically under the covers. In many cases, you don't even realize when there's been conflicts. The only time when the system will tell you that there's a conflict is when you actually tried to modify the same partition at the same time, a case where you should be told, no, 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 you cannot do that. Your data will be corrupt otherwise. So the final thing I want to talk about is handling massive metadata. The kind of cool thing about data lakes is you can store millions of Parquet files in them. And that's really awesome for collecting a large repository of data to do your machine learning on. But it also means that it can take a really long time to handle that metadata. And so the question is, how do we have Delta scale to these very large table sizes? And the answer is use Spark. We take metadata and we turn it into a data problem. We've already got a pretty powerful data processor here. So we can take this set of actions, add and remove and add and remove. We can write a Spark job that processes them and cancels out the adds and removes and comes up with a table of everything that is currently valid. We can write it out as a checkpoint. So a checkpoint says, this is the complete state of this table at this version. And so you do not need to read any of the transaction log previous to a checkpoint. You can just start with that checkpoint. And we store it in an efficient format like Parquet. So now when you actually want to run a Spark query, so let's say you have a giant table and it has 10 million files in it, but I want to query only yesterday. I just have a question about yesterday. We start by running a small Spark query that filters down that metadata set to find only the files that are relevant to your particular query. And then once we have that list, then we actually run another Spark query to actually go and process those files. But what this means is that Delta can easily scale to tables with millions of files and still handle the metadata. So we'll no longer have problems like too many partitions in the Hive metastore. So now I want to talk really quick about the roadmap, because like I said before, Delta Lake is a very new project that we just released a month and a half ago. But we've got a pretty exciting roadmap. So we just released 0.20 last week, which basically adds support for S3 and Azure Blob Store. So now you can use it in the cloud. In 0.30, we're going to be open sourcing all of the standard DML. So update, delete, merge, and we'll also be open sourcing the vacuum command, which allows you to clean up stale snapshots because you do not want to pay infinite amounts of money to EC2. And then finally, in the rest of Q3, we're going to be working on full DDL support and Hive metastore support, and also taking those update, delete, and merge DML commands and exposing them through the Spark SQL parser. So with that, I'd like to encourage you to check out our website, delta.io. It's got a quick start guide if you want to get started. It's got links to GitHub. There's also a Slack channel that we're super active on. So if you have any questions about Delta or Spark, I encourage you to go to there to talk about them. And there's also a mailing list. So please join the community. Tell us what you're looking for. And with that, I'd love to take some questions.
Offer the mic, but I don't know if we can get so.
Yeah. Yeah.
I understand how that would work currently adding reference.
That's a great question.
Does it stop the world process?
No, no, no. So yeah, so the question is with vacuum, how do you vacuum concurrently with other operations so that you don't want to delete, you don't want to vacuum something that is currently being written, for example. So the vacuum command is basically list everything on the file system, eliminate anything that is too new. So there's a threshold for how long a transaction can run for. And then we basically take that and we anti-join it with two sets of things. Files that are currently valid in the table and files where there is still a valid tombstone. So a file that was valid but was deleted recently. So there's basically two interesting thresholds here. Exactly, yes. So basically, the remove file action is a tombstone, and it records also the date that it was deleted on. And we keep that in the table until the tombstones go past the retention window. So there's basically both how long can a transaction run for, and how long do I want to keep stale snapshots for, and those are the two inputs to vacuum. Any other questions? Yeah, in the back. Yeah, that's a great question. That's one we've gotten quite a bit. So let me tell you a little bit about kind of the history of Delta. So when I build products, kind of one of the things I think about is how do I minimize the number of tuning knobs in the system? And I think this can actually be pretty powerful. An example I like to share is when we first created Delta, we had a bunch of people who converted their data from Hive input sequence format, something or other, into Delta. Did nothing else. Weren't using any of the other cool features of Delta. And their job went from I think it was 15 hours to under an hour. And I was like, well, I'd love to take credit for that. That was just using a good, efficient format. So that's why we only support Parquet today. It's a good choice. It works really well with Spark. The underlying transaction protocol actually has support for any file format that Spark supports. So Spark has this abstraction called a file format. It's what it uses when you say like .format read something. So CSV, JSON, Avro, Parquet, ORC, text. Any of those could work with the underlying transaction protocol. We don't currently expose that, but I'm totally looking for kind of use cases where that's important to figure out what the right way to expose those knobs are for. Yeah, right here.
I have a ton of data trapped into HTML. How can I post it?
Yeah, so the question was, if I've already got a bunch of data in HDFS, how do I use Delta? So there's kind of two answers here. One is if it's kind of stored in text or JSON or something like that, I would suggest you just do Spark read, Spark write to convert it into Delta. If it's already stored in Parquet, we have a command called convert to Delta that I think we're planning to open source in the near future, where basically all it does is list all of the files in the directory and create an initial transaction log entry for you. So that is definitely a use case that we're pretty interested in. I'm curious, is your data in Parquet, just as a data point? Yeah, okay, so yeah, I think in that case, convert to Delta is like the right answer. Yes?
Two questions, a quick one and a long one. Your last slide, there was a note on 0.3. Is there any features that are released?
Yeah, that's a great question. So when I'm talking about update, delete, merge, and vacuum, there's kind of two ways you could expose this. You could give somebody a function that they can call in Scala or Java, or you could create DML in the Spark SQL parser. So they could do like SQL update or merge into, using kind of standard syntax. There's not going to be a Spark release for another couple months. So in the short term, we're just going to expose Scala and Java APIs. But what we're looking to do is add full SQL support. So basically, we're going to work with the Apache Spark community to improve the SQL parser to support all of these operations, because Spark doesn't understand these today, and allow it to pass them down to us. So this is kind of like short-term, long-term plan.
My longer question was about incrementally updating it.
Mhm.
I guess it's kind of related. Source data is in database. Does Delta help you somehow with the problem of incrementally extracting dates to that source table?
Yeah.
Or do you still need to solve that as the source by adding, update triggers or whatever?
Yeah, that's a great question. So the question was, if I've got data that's in something like a SQL database and it's changing over time, how do I get that data into Delta? And does Delta solve that problem? And I think the answer is Delta does not solve that problem completely by itself. But I think the way that Delta helps you solve that problem is by integrating with Spark. I always view Spark as kind of the nice skinny waist of the big data system. It has connectors for almost every other system in the world. And so I've seen a couple of different ways where people solve exactly that problem. So one is you can take something like Debezium and use it with Kafka Connect, and you take your updates from the database, you feed it into Kafka, and then you use merge into to apply it to your Delta Lake. That's a pretty common pattern, and structured streaming supports this pretty well. Oh, Debezium is just a library that can, basically it translates the Postgres or MySQL transaction log into something that is readable. There's like this binary log that records everything that happens to your database. It's just a really easy way to do change data capture. And like at Databricks, we have a custom connector that does this for you, but you can also cobble this thing together with open source, no problem. And I think the magic that Delta is providing here is that merge into. That's something that was missing before. You could get this stream of updates, but applying it efficiently to a massive collection of data was very difficult. Here.
What manages metadata?
Yeah, great question. So the question was, what extra infrastructure do you need? You of course need a Spark cluster, but you also need Zookeeper or something like that. If you're running on a transactional file system, HDFS, Azure Blob Store, ADLS Gen 1 or Gen 2, you need nothing other than the Spark cluster. All metadata is stored in the file system, and we use that mutual exclusion trick to basically guarantee consistency. On S3, if you have a single cluster writing to S3, we can do locking within the JVM to provide it. If you have multiple clusters, that's something we're working on. You basically need some outside service, MySQL, Dynamo, Zookeeper, some simple thing to say this guy won transaction 1. So, and that's something we're working on, and we're actually, I'd love to have contributors who are interested in that. Multi-cluster S3 support. That's a good question. I mean, this is our short-term roadmap for Q3. Q4 is not decided yet. It's kind of based on how many people need it, and if someone is volunteering to build it. I think building it is actually pretty simple, and I'd be happy to talk about kind of the implementation details. It's like purely a team resource constraint thing that we don't have it today. And inside of Databricks, we have like a commit service to do this. So we have something kind of very similar. So we know how to build this, and I'm happy to describe it to you. Yeah, in the back. Yeah, so I mean, I don't want to, my goal is not to shill for Databricks, but I'll give you a really quick. Databricks is basically one of the companies behind Spark. We have a managed solution where we'll automatically create Spark clusters for you. We have notebooks and collaboration, and we have a managed version of Delta Lake where, we basically take care of the commit service on S3 and making sure it's the latest version, and we have a forked version of Spark that's a bunch faster. But our goal with this is the same goal that we had when we created Apache Spark originally. We want this to be the standard. We want open source to be, successful. We think that helps our business when that happens. So, basically the thing that we open sourced is the real scalable transaction log that you get inside of Databricks. It's just there's a platform around the Databricks version. Yeah, right here. Yeah, that's a great question. So I guess the question is there a way to sequence these? I've seen people use all kinds of different ways to do this. So I've seen people use Airflow. I've seen people use Oozie. Databricks has its own scheduler that you can use. Really, I think that Delta is basically the kind of toolkit, but we're not a scheduling engine. I would say the closest thing we do to scheduling is deep integration with structured streaming, where you can start kind of one type of computation, and Delta will continue to do that incrementally. But if you just want to schedule like an update to run every day, that's something like an outside scheduler would be used for. Over here.
So in the previous slide or two, you mentioned how JSON files help solve partition files and type problems.
Yeah.
Oh.
No, that's a great question. So basically the question was, you said you're going to integrate with Hive Metastore, but you also said the Hive Metastore is not scalable. Why? And that's actually kind of interesting because when I first started Delta, my goal was to kill the Hive Metastore. I was like, I hate this thing. It's causing me scalability problems. But I was wrong. I was missing something. The Hive Metastore is not only about storing metadata for a collection of files and storing partitions for a collection of files in your data lake. The Metastore is also about data discovery within an organization. It's a central place where you can create what I think of as symlinks to data that's stored in your data lake. And so the way Delta interacts with the Metastore is really like a symlink. The only thing we store in the Metastore is a name and a pointer to a transaction log. The transaction log is the source of truth for what the schema is and what partitions are there. But we do allow you to do create table, alter table, all the kind of standard DDL stuff, and define that table in the Metastore. And we're currently working with Starburst, the Presto company, and other people to figure out how to basically, once something is in the Hive Metastore, allow other engines to read from it as well. Yes, you absolutely, basically kind of the core trick here is the Hive Metastore operates at the partition level, and the way that we get ACID semantics is we operate at the file level. You could never put all of the files in the Hive Metastore because of scalability problems. So you have to understand the transaction log. But there's a bunch of interest in building different connectors to do that right now, and that's something we're super committed to in the project, is to helping those people build those connectors. Any other questions? Yeah, maybe one more. What's that? So the question was, what is the main language it's implemented in? I'm a Scala fanboy, so it's written in Scala. Both. Yeah, we cross-compile against both of them. Yeah, one more question, and then we'll call it. Yeah, great question. So the question was, I know you've got this paid version of this. What's not in open source? So the answer today is there's a bunch of stuff because we open sourced this a month ago and we're like, it's hard to disentangle code. But let me tell you my philosophy on open source for this project, and that is that APIs need to be open. Any API, any program that you can run inside of Databricks, you need to be able to run outside and get the same correct answer. So update, delete, merge, vacuum, streaming, batch, time travel, all those things that kind of change the correctness of your answer will be in open source. And we're kind of, basically my team's next couple of quarters is just taking our proprietary bits, disentangling from the platform, and putting them in open source. Now, Databricks has a forked version of Spark, so Delta might be faster inside of Databricks. But in terms of like you being able to write a program and getting the correct answer, we are committed to putting everything in open source. And with that, I think I'll call it. I'll stick around if there's more questions, but thank you very much.
So thank you, Michael. That was the only secret we have obviously you're welcome to hang around, socialize, network, or whatever. There's one request I just want to make quickly, which is that if you guys have some ideas or you're willing to host,
Yeah, I'll do that.